Good morning, everyone, and let's start off with a video for the introduction of the company.
Welcome to the world of sapphires. Valuable, unmatched beauty, rarity and purity are the ultimate qualities of this precious gemstone. Virtually unscratchable, sapphires are the only natural material on Earth as hard as diamonds. In nature, sapphires are formed from high-purity alumina deep in the Earth's crust. Like any naturally occurring gemstone, heat, energy and pressure over millions of years stimulates the growth of these natural sapphire crystals. Today, mankind has the technology to recreate the formation of sapphires using high-purity alumina under intense pressure and heat. The formation takes place in high-tech furnaces where large single sapphire crystals are grown from high-quality alumina. From these crystals, sapphire wafers and sapphire glass are extracted using diamond cutting technology. These synthetic sapphires, like the natural sapphire gemstones, are highly valuable and prized. Today, synthetic sapphire is playing a large and growing part in our everyday modern lives. Sapphire wafers are used in the manufacture of cost-effective, energy-efficient LED lights. LEDs, the lighting of the future, offer huge energy savings and are rapidly replacing traditional light globes around the world today. Semiconductors in our electronic devices, phosphor-plasma televisions and scratch-proof watches are some of the many applications that belong to the sapphire family. Smartphone manufacturers are already making the exciting transition to the unscratchable sapphire display screens. We all look forward to a sapphire future of unscratchable glass. To meet this sapphire future, Altech Chemicals, an Australian company, is aiming to be the world's leading supplier of high-purity alumina. Altech has rapidly grown to consolidate its strategic advantage through the rapid development of its kaolin mine in Western Australia and its proposed high-purity alumina chemical facility in Johor, Malaysia. The company's proposed state-of-the-art production facility will produce high-purity alumina, specifically designed for the synthetic sapphire market. Well positioned in the Asia-Pacific region, customers around the world will trust the quality and reliability of Altech's high-purity alumina products. Altech's proposed expert customer support and state-of-the-art packaging and distribution service will be second to none. Altech Chemicals is aiming to be the leading supplier of the key ingredient for sapphire glass, high-quality pure alumina. Altech Chemicals, meeting a sapphire future.
Okay, so we are listed on the ASX. The ticker code is ATC, so remember it's a bit like the ATO, but we're much friendlier. So as you see in the video here, sapphires are nearly as hard as diamond. It's formed under pressure and temperature. On the hardness scale, it's number 9 compared to diamond, which is 10. So if you're thinking of buying your spouse a wedding anniversary gift, don't forget about diamonds, go and buy sapphires. But actually forget about sapphires, buy some ATC shares, they're probably worth a hell of a lot more down the track. So what we intend to make is a high purity alumina. It's 99.99%. As a comparison to the smelter grade alumina like the Alcoas and Worsley produce, that's about 99.5%. But the problem with that process, it uses sodium hydroxide as part of the Bayer process. And sodium gets locked into the crystal structure, is very difficult to remove. Sodium is a big problem for the electronics industry. So if you're going to make high purity alumina, you want a process without sodium. So that's a good point. The price of this material is about $23,000 a tonne. So typical of these high purity compounds like silicon and so on, the price is exponential. So smelter grade alumina might be $400 a tonne, 3 nines is $6,000 a tonne. Our product is $23,000 US a tonne. So that's our target business. And the way they make this is they buy the high purity alumina powder, They heat it up to 2,000 degrees, it melts, and it forms a single crystal. It grows that crystal over 20 days, and you get a crystal ball like the one in there. And basically what they do is they cut the shapes from it using diamond saws, and you have these sapphire wafers. Now the sapphire wafer is the building block of the LED industry. So they put electronics on it, chemicals, and that becomes a semiconductor. And if you apply electricity to it, it actually produces light. Now the beauty of LEDs is it's nearly 90% more efficient than the normal light globe. So in a normal globe, you're actually producing heat to produce light, where these semiconductors basically are producing photon lights without heat. So 90% of your energy goes to producing light. And you may see on the right-hand side these bars, they have these old type of globes. They're actually not filaments. If you look close enough, they're actually little LEDs. So very efficient lighting. The sector is split up according to this. About 57% is used in the LED industry, about 22% in the semiconductor industry, phosphor TV screens, etc. But as you can see on that pie graph, lithium batteries and smartphones are not featured. They're the growth industries. Currently, about 25,000 tonnes per annum are used around the world today. It's growing at about 17% year on year, generally driven by the LED industry, and then now following up by the lithium battery sector. That's the forecast growth to 2024. You can see very strong growth there. And even if you track the LED shipments or production in the world today, it's something like 864 million LED units being produced, expected to climb to 4 billion by 2024. Now, this is a very exciting area of growth. It's the lithium battery. So you've heard recently with the batteries catching alight. Well, as these batteries got larger, the large format batteries, they tended to overheat. So when you overheat, you get a thermal runaway. And when you get a thermal runaway, what actually catches a light, the anode and cathode are really not combustible. It's the separators, the plastic separators that separate the anode and the cathode. And now these large battery suppliers are demanding that these separators be fire retardant. And what they're doing is they're coating high purity alumina in these separators because alumina is a very good fire retardant. And this is so how hard are these sapphire glass? This is a very scientific scratch test with the Apple Watch glass face. So if you're actually wearing a watch, if you haven't got any scratches in glass, it's most likely sapphire glass. And if you look in the back of the watch, you'll say sapphire glass. Now, if you don't believe me, try when you get home, put a drill through it. If it goes through your hand, you start bleeding, it's not sapphire. So 70% of HPA demand is used in the Asia-Pacific region, which is where you expect most of the electronic manufacturing takes place. Our project, basically, we have a deposit in Western Australia and our proposed plant in Johor in Malaysia. So let's look at the current producers. There are companies like Sumitomo, Sasol, Pangda, etc. So they are large chemical companies. And the way they make high purity alumina today is they use aluminium metal. Because to meet the specification of 99.99% purity, they buy a high purity aluminium metal, they dissolve it using alcohol, hydrolyze it, and they make this material. Now, if you think about it, it comes from bauxite. Aluminium metal comes from bauxite. They make smelter-grade alumina. They buy it. They put a lot of electricity in it, and they make aluminium metal. And these guys buy it and produce alumina. So it sort of doesn't make sense, a very expensive process. I guess our process is a disruptive technology. We're starting straight from the ore to the 4 nines in one single step, bypassing the alumina. And the only reason we can do that is we start with a very pure ore body, which is a kaolin deposit. As you can see the colour of it, there's hardly any iron in it, and we can achieve that in one single step. You look at the analysis of kaolin versus bauxite, we've got about 0.7% iron compared to bauxite's about 21%, and very low impurities. Now kaolin, as you know, is used as a whitening agent for paper, ceramic and so on, but we're using the kaolin for the alumina content. The deposit is from West Australia. We own the deposit. It's something like a 250 mine life, and we have the lease granted. The process we use is a hydrochloric acid leach process. So it's the same acid you use in your swimming pool. It was developed in the 1980s by the alumina industry and the US government. The US never had a lot of bauxite deposits, and they said, look, we've got plenty of kaolin, like the Georgia kaolin. Can we develop the technology to supply our aluminium refineries? And the technology was developed, it worked really well, but unfortunately, at the time, it couldn't compete with the Bayer process on cost basis. But if you think about it, it's actually very good at making high purity alumina because you don't use any sodium ions. But again, in the 1980s, there wasn't a lot of demand for high purity alumina. Not a lot of LEDs around, not a lot of sapphire glass around. So because of the demand today of high purity alumina, we are building this project with a kaolin deposit. This is the plant that we propose to build in Malaysia, about 80 million US dollars, producing 4,000 tonnes per annum of high purity alumina. We completed a bankable feasibility study, so some people might be interested in the financials. Roughly 80 million capex, the payback is about 3.7 years. The pre-tax NPV at a discount rate of 9% is about 357 million, very attractive numbers. And the internal rate of return is about 33%. Well, the operating cost is about $9,000 a tonne. Most of the competitors are running at about 17,000, so a dramatic change in operating costs. Sale price of 23,000, the margin is about 14,000 tonnes per annum. Now, 14,000 tonnes times 4,000 gives you an EBITDA per year, throws off around 56 million per annum. So very attractive number. So why are we so cheap? Firstly, we own our feedstock. So you must understand the chemical industry, chemical suppliers tend to buy their feedstock and convert it. I guess we're a mining chemical tech company. We own our own feedstock. We use hydrochloric acid, which can be recycled in our plant, and we're in a low-cost country like Malaysia. And that's on the bottom there's a graph of a cost comparison done by Persistence. You can see where we sit compared to the conventional process. We recently signed an offtake agreement, a 10-year offtake agreement with Mitsubishi to secure 100% of the product. We are in the debt funding stage. We are very advanced. We are obtaining a debt of 70 million from KfW IPEX Bank, of which 60 million is actually export credit cover. So what that means is that it's underwritten by the German government because 60% of this plant actually come from German suppliers. And so we get very low interest, something like LIBOR plus 2% on our debt. And we hope to finalise this term sheet by the end of this year. Some of the updates. We are in the due diligence process. We've had independent consultants go through. There are no fatal flaws identified. We've had a positive pre-assessment by the German government, and we are moving through the approval process. Very advanced in our detailed design. The design is done by our EPC contract is a company called M+W Group, which is a German company, and our permitting and our process in Meckering are continuing. So the company itself, in the last 12 months, the market cap's triple. We've built our shareholder base from something like 600 to 1,500, and we also have recently raised 10 million with some very named institutions on there. So in summary, this is the time frame to market. We hope to finalise our debt early 2017. Our project equity part will come in around Q2 2017. Hopefully our site works commences in Q2 next year, 18 months construction, about 6 months commissioning, and first product out in 2019. So thank you very much, ladies and gentlemen, for your time.
Thanks, Iggy.